3, 2, 1.
Oh! Bang goes the theory. It's going to get a little bit frosty. I'm making snowballs at the very edge of the solar system. Lurking out there are literally trillions of these dirty great snowballs, comets in waiting. Liz nearly freezes to death. And Jem tries to kill us all with a boat made of ice.
King of the world!
That's Bang goes the theory.
Oh, man.
Putting science to the test.
A lot of people think of concrete as a bit dull, but it's a wonder material. The Romans used it 2,000 years ago, and the Pantheon in Rome is still the largest unreinforced concrete dome in the world. Inspired by that, I thought we should get up to our own outrageous concrete-based caper. Concrete is essentially little stones like this, tiny grains of sand like these, bound together, glued together by a glue, cement. Now, you would have thought that the glue would be the strongest part of that the glue on its own would be stronger than the glue with all this rubbish in it. But it isn't. It's very different. That's a pure cement dome. Let's see what it can handle. There's a little oculus for any Romans watching. Not as tough as it would look. The thing with cement is it's hard, but quite brittle, which means it breaks relatively easily. Let's see how that compares with concrete. Well, that's considerably tougher. I mean, the Romans even used to add just old broken pots and tiles to cement to make their concrete. And it seems like it's the impurities that give it its strength. It's like cement's rubbish, you add rubbish to it, and it becomes brilliant. How's that? To find out, let's cut my dome in half. There we go. Our concrete dome. You can see here, there's our bits of broken pots. It's actually an old plant pot of mine. And it's much stronger because what happens is if a crack starts to form, it'll start to spread through the cement. But when it reaches one of these stones, the crack comes to a dead end. It's no longer a sharp point. Consequently, all the tiny little cracks that appear never get the chance to expand out into big cracks that go through the whole piece of material. But my concrete caper isn't going to be based on cement. I'm going to make my concrete out of ice and take it to sea. Back in the Second World War, when there was a lack of steel, someone came up with the idea of building aircraft carriers out of pure ice. Then this chap, Geoffrey Pike, suggested adding wood pulp to ice to make a kind of concrete, and that's pretty much what I want to try. Now, I don't know if this will ever really work, but I don't think it should be left like that. It's too fascinating a concept to leave for history. For me, there's such a hook about making a ship to sail on the sea that's made from ice. So, I want to make one. First, a basic experiment. Just like concrete, Pykrete is a mixture of ice, the matrix or glue that keeps the whole thing together, and a reinforcement. Change the reinforcement you use and the properties of the concrete will change too. So let's do some tests. First up, plain ice. Not exactly what you'd want to make an aircraft carrier out of. Next, it's ice and wood chips, which is much stronger. Right. Finally, it's ice mixed with hemp fibres. Could they be the strongest of all? Let's give it the full weight. Oh! Now, what happened there was the hemp didn't move at all. It was the cable tie that broke. Chuck a nut. 25 kilo bag of sand, 75 kilo bloke, nothing. Perfect. But just building a strong boat is of no use if it melts as soon as it hits the water, which is why I've had to turn my kids' paddling pool into a test tank. Naked ice melts very quickly in water, whereas the ice sawdust and ice hemp mix, as the outer layer of ice within it melts away, it almost leaves itself with a woolly jumper, insulating the ice on the inside. And for the kind of environment we're looking to set our boat into, it needs as woolly a jumper as possible. But what's interesting is what happens when you speed things up a bit. I'm hoping to buzz along at about 8 knots or so. And turning up the speed of my test rig shows there's a real difference between the two main contenders. Conclusion there is, at low speed, hemp and sawdust mixed with ice are pretty much neck and neck. But turn the speed up and the sawdust disappears fairly quickly. The hemp and ice are the clear winner. It may not look pretty, but for my next trick, I'm going to turn this hairy mess into the largest ocean-going ice boat ever made. The idea is that all 4 Bang presenters will sail from Gosport Marina and head out over the water to Portsmouth to take a salute from the Navy's finest. Now, the only way we're going to find out if all that works is to build the boat and drop it in the drink.
Oh, yeah, no, that'd be good. We'll have a nice day. We'll invite Dr. Yan. We'll have a day out.
I'm sorry to bring this up, right? But if my memory serves me correctly, a lot of your builds end up with you in the water getting soaked, right?
It has happened.
Yeah. So the idea of us sinking in the middle of the cold sea in an ice boat just isn't quite my idea of a fun day out.
See, I think that's really funny.
I'm sure you do. So look, no offence, Jem, but I'm going to get myself prepared. Volunteer lifeboats in the UK are called out around 8,000 times a year to fish people out of the drink in all weathers. And today I'm heading out on exercise with the crew of the Portsmouth RNLI.
As today you can see there's such lovely weather, the water looks extremely inviting. You can be fooled into thinking the water is actually a lot warmer than it really is. I think the best way is for you to experience it firsthand.
What are you talking about?
I think we need to get you in the water.
Seriously? But it's how cold is it?
It's about 13 degrees today.
Ah, Toby.
Follow me in.
Oh, I can't believe I'm doing this.
Can you jump?
That's not even funny. Oh my God. I can't. It's really cold.
That's the cold shock response in your body working.
I'm not really liking this.
You are hyperventilating and it's completely out of your control. At the moment, that life jacket's keeping your head above water.
Yeah.
If you had fallen over not knowing about it, you would have gone under and possibly not come back up.
My heart is beating through my chest. It's so cold.
Yeah, your heartbeat will increase massively as you go into the cold water. The shock will increase your blood pressure. And potentially you could have a heart attack if you're not fit and healthy.
It's all right for Toby. He's in a protective suit, which makes all the difference in 13-degree water.
The cold shock response is what's going to get you first as you hit the water first of all. Hypothermia comes on after that, once you've been in the water 25 to 30 minutes. This is the main killer.
Can I get out now? Please, can I get out now?
Oh, okay. Get you out. 3.
Over half of the people who lose their lives in immersion accidents die within the first 3 minutes as a result of the cold shock response, long before a lifeboat could possibly reach them. But at Portsmouth University's Extreme Environments Lab, Professor Mike Tipton and his team can demonstrate something very interesting about the cold shock response, which may also help me prepare for Jem's ice boat adventure.
The good news is that with repeated exposures, you get used to the cold shock response. It habituates. You get used to going into the cold water.
This is where I come in.
Yes.
Because you're going to demonstrate it with me today, which I'm clearly delighted about.
Yes, we're going to do some repeat immersions on you and just see what your cold shock response is and how much we can reduce it.
Oh, excellent. To monitor my body's exact response, I'm rigged up to a heart rate monitor and a breath analysis machine.
Ready? Okay, Martin, do you want to...
The water in here is about 13 degrees centigrade, roughly the average sea temperature for the UK.
3, 2, 1, go.
My heart rate, previously a nervous 80 beats per minute, shoots up to 125, which is very high when you're just sitting still. And my breathing rate rockets from 13 breaths per minute to 68. That's more than 1 breath per second.
Okay, and that's a minute. Mouthpiece out. Okay, Liz, now on that scale of 1 to 6, where 6 is unbearably uncomfortable. 6.
I can quite safely say, Mike, that is the worst thing I have ever done in my entire life.
You now understand what we mean by the first minute or two of immersion being the most dangerous response.
I was amazed at how I just could not control my breathing at all. I was properly hyperventilating, wasn't I?
It only takes you to be breathing in as a wave breaks over your face, and you've aspirated the 1.5 litres necessary to drown.
But I'm here to improve my response in preparation for Jem's challenge, and Mike thinks he can reduce it by up to 50%. And that means I've got to go back in again and again.
How many more dunks do you think I need?
Well, I think you probably need a total of 5 or 6, so we've got a few more to go yet, but
Okay.
It will now start getting better.
Do you promise?
No.
Over the next few hours, Mike dumps me in the water and warms me up again another 4 times.
And time to do the comfort.
5.9, 5.8, 5.9, 5.9.
You can see how dramatically my skin temperature drops on this thermal camera. I'm the same temperature as the water. Water conducts heat over 20 times better than air, so it's incredibly efficient at stealing the heat from my body. That's why water at 13 degrees centigrade feels so much colder than air at the same temperature, and why it's so much more dangerous.
5, and a push 4.9. Drop it up.
That's good. Nice to sit and rest.
But by my 5th time in the cold water, my body's getting used to it. My heart rate only goes up to around 90 beats a minute instead of 125, and my breathing only climbs to 32 breaths a minute instead of 68. And it doesn't feel as bad anymore either.
Am I very uncomfortable or just uncomfortable? I'm 3.5.
That's really good.
Am I habituated?
Yes.
Come on, get me out of here. Bring on the Pie Creek boat, I'm ready for you.
You're a brave woman, Liz. Okay, so let me ask you this. How long are you now habituated for?
For around about a year, but I tell you what, I am never doing that again.
horrible?
Oh, it was horrid. So when the year runs out, it runs out. That's it.
So I've got a year, basically, to chuck a bucket of cold water on you and you'll be okay.
That's not even funny, Campbell.
Okay, now, as tonight's theme is all about ice,
Yeah.
have a look at this, the oldest ice in the solar system. 4.6 billion years ago, when the sun first sparked into life, it was surrounded by a vast cloud of dust called the protoplanetary disk. And it's this stuff, pulled together by gravity, that eventually went on to form the planets of our solar system. But not all of that cosmic rubble was captured by the fast-forming planets. Way out there, extending right to the edge of the sun's gravitational pull, some trillion or so kilometers away, lies the Oort cloud, the remnants of the protoplanetary disk from which the planets formed. Here, the rubble orbits in the form of frozen lumps of matter we call comets. Come with me on a journey to the very dawn of the solar system. Now, this humble freezer is like a portal back in time, and just like some of the nasty things you find in the back of your freezer, Lurking out there are literally trillions of these dirty great snowballs, comets in waiting. But unfortunately and annoyingly, we're never ever going to see them. Even if you did have some kind of telescope powerful enough, they're still not going to be visible. Far from being great streaks of white light we sometimes see whizzing around our sun, most of the time we can't see comets at all, and that's because out there on the frozen edges of our solar system, comets are so black that no optical telescope could ever make them out. So to give you a bit of an idea of just how black comets are, have a look at this. It's a piece of asphalt from the road. Now this asphalt reflects about 7% of the light back. It's very, very black. But comets, on the other hand, reflect only about 3 or 4% of the light back. They are very, very dark indeed. In fact, they are the darkest things in the entire solar system. Okay, so how do they change from dark frozen lumps over a light year away to bright white streaks in the night sky? To find out, I've recruited one of the world's foremost experts in comets, Professor Amy Lovell. Now, I understand that comets are obviously they're very far away in the Oort cloud and they're very dark, so we can't see them. But how on earth do they get from the Oort cloud to where we can see them, and how do they actually become visible?
Well, space is crowded. Even though it's big, it's crowded and things interact with each other. You get a gravitational pull or a collision or something like that, and the comet can fall towards the sun, and then it goes into orbit.
Okay.
And when it goes into orbit, then it comes near us and we see it.
So how do they get from very, very dark, from being sort of the darkest things in the solar system, to these beautiful, bright, glowing, shiny things that we're familiar with lovely tails?
Well, that's just how the light interacts with what it's made out of. Let's make one and see.
We can make a comet.
Let's make a comet.
Okay. So how do we do that?
Okay, the recipe begins with water.
So this is regular tap water.
H2O.
H2O, nice. Say when?
Pour it all in.
All of that in there?
All of that.
Okay.
And then the comet has particles in it, dirt.
Right. Bit of sand. So this is, presumably this is why comets are dark.
They have dark particles in them.
Okay. So,
and then a little bit of ammonia.
So this is just window cleaning stuff, ammonia, bit of that.
Don't clean your windows with a comet though, it's probably not a good idea.
Okay.
That's enough, I think.
Okay.
And some organic matter, for which we will use soda.
Okay.
That's good.
There we go, okay, good.
Okay, and then, of course, the comet has to be frozen, so we need ice.
Okay, so
there's dry ice here. Safety first, let's put the goggles on.
all right, okay.
And gloves.
Here we go. Right, okay, so...
And see, it's outgassing.
Dry ice, that's frozen carbon dioxide.
Frozen carbon dioxide, much colder than regular ice. Okay, now mash it. There you go.
So that dry ice is going to freeze all that liquid together. Oh, man!
Make sure you get the liquid in the corners there.
Yeah. Wow, this is dirty. This is really...
You're making a dirty snowball.
Wow, look at that!
That's the comet, and so as that comes closer to the sun, as it falls towards the sun, it gets vaporized. As the gas vaporizes off, it takes some of the dirt with it.
Right.
The sun shines on it and it reflects. So you see that, and then as the solar wind, particles streaming off of the sun, hit the things that are evaporating from this comet, it goes into a tail.
Kind of what like it's doing now. I mean, if I blow on that.
Yes, yeah, you're acting like the solar wind, and it's vaporizing. There you go. You're creating the beginning of the tail.
Out there in the Oort cloud, it's only about 4 degrees above absolute zero. But as a comet falls towards the sun, it begins to warm up. Its icy contents vaporizing to form a trail of gas and dust hundreds of thousands of kilometers long. So how much material is actually being vaporized off a comet?
An active comet can lose 3,000 kilograms every second.
Which seems like a lot, considering that comets are only in the magnitude of a few kilometers in size.
It is an awful lot. Comet Halley, we know of at least 30 orbits it's gone around the sun, and it's probably lost more than 2 kilometers of its surface.
So what's the ultimate fate of a comet? Do they just fizzle out into nothing, or...?
Some of them will crust over and die, and then some of them will fizz and literally explode or break up.
So it's not good, ultimately. Poor old comet.
Poor comet.
What I find so wonderful is that the great nomads of space, the comets, are made of just simple stuff you can find here on Earth.
Absolutely, we're all made of star stuff. And the fact that you can just knock one up in your kitchen, I think is great.
Nice. The best bit of the film for me is the explanation about the tail. I never knew that.
I know, but it makes total sense, doesn't it, when you think about it?
Absolutely, yeah.
Anyway, talking of large frozen objects causing trouble here on Earth, it's back to my ice-based boat. In part 1, I discovered just how strong a composite of hemp and ice could be. Further tests showed that its woolly jumper effect meant it lasts a lot longer in water than normal ice. But now for the big one. Will it float? The original idea was to make aircraft carriers out of the stuff. Well, I'm not going that far, but it's a good bet that my boat, Pike's Folly, will be the largest ice boat ever to take to the sea. At the moment, it looks like something Noah would have built, but this mould is all about keeping the flood in rather than keeping it out. When we line this and fill it with water, it's got about 7.5 tons of water pressure force pushing that way, and about 2 tons pushing out the back, which is like hanging a truck from each side and a van from the back of it.
The final touch is line the whole thing with plastic, then pop in 3 large negative moulds, which will form the compartments where the 4 of us can stand.
Sweet, nice, really nice. These are going to be the walls of the boat, and at the moment we're just packing them with hemp fibres, but all those fibres are going to get glued together with frozen water.
Once we've stuffed it with half a ton of hemp, we can fill the mould with 5,000 litres of water. When it's all frozen, it should be stronger than concrete and last considerably longer than ordinary ice. But that's if freezing it to minus 25 degrees does not destroy it first.
Over the next week, there are going to be glacial forces acting on that. The kind of forces that shape mountains, that shape plains, that split rocks. I can't imagine that wood is going to hold in every single place.
My worry is that our scratch-built mould may not withstand these huge forces and split before the ship is fully frozen. If it does, we could return to find just a giant frozen puddle. But somehow it didn't. After 3 weeks in an industrial freezer, 5.5 tons of water and hemp has turned into Pike's Folly. Everything is going to plan. She is incredibly strong. Even cutting through her transom to fit mounts for her engine takes a full-on chainsaw. And as she's loaded into the freezer lorry to be taken to her launch site at Gosport, I feel she's ready for anything.
That's our ship arriving.
Oh, I'm so excited. We're finally going to see it. It's a woolly mammoth.
Now Pike's Folly is out of the freezer lorry, she's melting, and the clock is ticking to her inevitable demise. The most critical thing is to get the engine and steering system rigged in double quick time. It's crucial that the engine mountings are above the waterline, but the prop itself is as deep as possible. After a record-breaking fit-out, we're ready for the launch of what I'm sure is the largest seagoing ice boat ever built. With a 30-centimetre thick hull, we should get 2 hours life from the moment it hits the water.
The prop's got to be at least underwater.
As she floats off her mould, Pike's Folly is finally free.
Hey! Where's the champagne? Where's the champagne?
Hey! Right. We name this ship Pike's Folly.
Is it going to be a nice buffet trolley car coming up and down?
Probably, yes. Around about halfway. I'm terrified that we're not going anywhere yet.
Go, Dallas. Go.
We are good. Oh, it's the handling of this is precision handling.
Despite all my smiles, deep down, I'm quite a worried man.
Alice Campbell! This is amazing now.
Pike's Folly was slightly lower at the stern than we'd expected, which meant the engine mountings were just below the waterline. But soon, we had other worries.
Is it steering okay?
Yeah, are we going towards those yachts there, Dallas?
I know, I'm trying to steer.
It's impossible to steer it. I'm doing my best.
Either Dallas had no idea what he was doing with this 5.5-ton craft, or it's a lot harder to control than anyone had first thought.
Yeah, straight from there.
Still, with a few scenic detours, he finally plucked up the courage to give her some welly. And for a while, she behaved. But just for a while.
Right hand down, right hand down, right hand down a little bit.
Okay.
Reverse, reverse, reverse.
It's in reverse. It's in reverse. It's in reverse. Okay.
Reverse.
It's in reverse. It's in reverse. It's in reverse. Are you all right?
Despite the ram raiding, we had to press on.
The boat's all right that we hit.
Dallas was so focused on his driving, he failed to mention the engine mountings had begun to leak and the stern compartment was filling with water.
Another 40 minutes, and then we're in the soup.
We had to speed up, so we took on a new skipper from the RNLI.
Do we need any bailing in there?
We've got so much water in the back here.
But the extra weight at the back only made things worse. What started as a trickle through the transom became a deluge.
Can you get Dallas to move forward?
But at least we made some progress towards our destination, HMS Diamond, whose finest were lining up to salute the genius of Geoffrey Pike.
Check this out, guys.
And the folly of Bang.
Here we go, look.
Whoa. Whoa.
Sadly, it was a compliment we were unable to return, as no sooner had they doffed their caps, our engine cut out.
Dallas, I'm going to get right to the front while you bail that out, because
There's a submarine there. Maybe we should go see that.
The Pykrete was holding up just fine, apart from the crucial little bit around the engine mounts.
There's loads of water in the back, so the guys are trying to deal with it with the electric pump.
From now on, we were in survival mode.
I'm taking it away!